The quantum apocalypse is not a question of if, but when. For decades, the entire digital world has rested comfortably on a foundation of number theory. Specifically, we rely on the difficulty of factoring large integers, known as RSA, and solving discrete logarithm problems, known as elliptic curve cryptography. These mathematical padlocks secure everything from your personal bank account to top-secret state intelligence. But in the quiet, supercooled labs of IBM, Google, and various nation-states, a new kind of beast is waking up: the quantum computer. When a sufficiently powerful quantum computer comes online, running Peter Shor's algorithm, it will not just pick these locks, it will dissolve them. The encryption protecting the entire history of the internet will be rendered transparent. This is the store now, decrypt later threat that keeps cryptographers awake at night. Intelligence agencies are already harvesting encrypted traffic today, storing it in massive data centers, waiting for the day they have the machine that can read it. But there is hope. It comes from a branch of mathematics that traces its roots back to 18th century stackings of cannonballs, yet has evolved into the most cutting-edge shield we have. It is called lattice-based cryptography. This is the story of the mathematical shield that will save the internet. To understand why lattice cryptography is quantum resistant, we must first visualize what a lattice actually is. Forget complex formulas for a moment, and imagine a simple two-dimensional piece of graph paper. A lattice is simply a grid of points that repeats infinitely. In 2 dimensions, it looks like the intersections of the lines on that graph paper. You can describe this grid using 2 vectors, which you can think of as arrows originating from a central point called the origin. These are called the basis vectors. By adding and subtracting these arrows in whole number combinations, you can hop from the origin to any other dot on this infinite grid. In 2 dimensions, this is trivial. If I asked you to find the shortest arrow that connects 2 points, you could just look at the paper and measure it. If I asked you which dot is closest to a random point on the paper, you could see it instantly. But cryptography does not happen in 2 dimensions. It happens in 500, 1000, or even 20,000 dimensions. In high-dimensional space, human intuition breaks down completely. Concepts like up and down become meaningless. The volume of space explodes exponentially. A high-dimensional lattice is a chaotic, dense cloud of points that looks less like a grid and more like a star field viewed from hyperspace. Lattice cryptography relies on the fact that finding your way around this high-dimensional web is excruciatingly difficult. There are 2 hard problems that form the bedrock of this security. The first is the shortest vector problem, or SVP. Imagine you are standing at the origin point of a 1,000-dimensional lattice. Your goal is simple: find the lattice point closest to you, other than the one you are standing on. In 2 dimensions, you just look. In 1,000 dimensions, you are effectively blind. The basis vectors you are given as a map might be incredibly long and skewed, zigzagging wildly through space. To find the shortest connection requires checking an exponential number of combinations. Even a quantum computer, which excels at finding periods and functions, which is the specific weakness of RSA, struggles to find short vectors in this geometric mess. The second hard problem is the closest vector problem, or CVP. Imagine you are dropped at a random point in space that is not on the lattice. You are asked to identify which lattice point is closest to you. Again, in high dimensions, this is a nightmare. The nearest point might be 1,000,000 miles away in one direction, but the skewed geometry of the lattice makes it mathematically close. These problems are nitrogen monophosphide hard. They are the mathematical equivalent to finding a specific grain of sand in the Sahara Desert, assuming the Sahara is 500-dimensional and constantly shifting. While lattices were studied by giants like Gauss and Lagrange in the 1800s to solve number theory problems, their use in cryptography is a modern revolution. The timeline of this shield is fascinating. In 1996, Miklos Ajtai changed the world of cryptography forever. He proved a theorem that is considered the holy grail of security: the worst case to average case reduction. In most crypto systems, we hope that the specific key we generate is hard to break. But sometimes, you might accidentally generate a weak key. Ajtai proved that if you can break a random instance of a lattice problem, meaning the average case, you can break every instance, including the absolute hardest ones, the worst case. This implies there are no weak keys in lattice cryptography. If the system is secure at all, it is secure everywhere. 2 years later, in 1998, 3 mathematicians named Hofstein, Pfeiffer, and Silverman introduced NTRU. It was efficient, using polynomial rings, a structured type of lattice, but it lacked the rigorous security proofs of Ajtai's work at the time. It was the punk rock of lattice crypto. Fast, effective, but looked down upon by the theoretical elite. Ironically, NTRU's core ideas would later be vindicated and absorbed into modern standards. Then came the revolution in 2005. Oded Regev introduced the learning with errors problem, or LWE. This bridged the gap between abstract lattice theory and practical encryption. LWE is surprisingly simple to explain. Imagine I have a secret system of linear equations. High school algebra tells you that you can solve for the unknowns easily using Gaussian elimination. But what if I add a tiny bit of error to each equation? If 2x plus 3y equals 10 becomes 2x plus 3y is approximately 10.1, the clean geometric lines become fuzzy clouds. Solving this noisy system to find the secret variables turns out to be computationally equivalent to solving the hard lattice problems like the shortest vector problem. Regev proved that learning with errors is as hard as quantum hard lattice problems. Finally, in 2009, Craig Gentry used lattices to solve a problem that had stumped cryptographers for 30 years, fully homomorphic encryption. This allows computers to process data while it is still encrypted. You can send your encrypted medical records to the cloud. The cloud analyzes them and sends back the result, without ever seeing your actual data. Lattices made this possible. Recognizing the quantum threat, the National Institute of Standards and Technology, known as NIST, launched a global competition in 2016 to find the successors to RSA and AES. It was a bloodbath. Dozens of algorithms entered, few survived. The competition pitted different mathematical families against each other. There were isogenies, which were elegant but slow, and eventually broken by a surprise attack in 2022. There were multivariate systems, which offered fast signatures but required huge keys and had fragile security. One major contender, Rainbow, was broken by a laptop. There were code-based systems, which are very secure but require encryption keys too massive for modern internet traffic. And then there were lattices. Lattices occupied the Goldilocks zone. They offered balanced key sizes, blazing fast performance, and strong security proofs. On August 13, 2024, after 8 years of scrutiny, NIST finalized the first batch of standards. Lattice cryptography emerged as the overwhelming winner. The first winner is FIPS 203, formerly known as ML-KEM, but previously called Crystal's Kyber. This is a key encapsulation mechanism. It replaces the Diffie-Hellman key exchange. It is how two parties establish a shared secret to encrypt a conversation. It uses module LWE. The word module means it works over lattice structures that have a bit of algebraic symmetry to make them smaller and faster, but not so much symmetry that it introduces weakness. It is blazing fast, often faster than the elliptic curve systems we use today, with reasonable key sizes of around 800 to 1500 bytes. The second winner is FIPS 204, formerly ML-DSA, previously known as Crystal's dilithium. This is for digital signatures. It proves that a message came from you and hasn't been tampered with. It replaces RSA signatures. It uses a paradigm called fiat shamir with abort over module lattices. It involves rejecting or aborting signatures that might leak information about the secret key, ensuring the output distribution is uniform and secure. It offers strong security and high performance, making it the primary workhorse for the future internet. There is also a backup called fluorine mononitride DSA, formerly Falcon. It uses NTRU lattices and is incredibly compact, but it is harder to implement securely without leaking information via side channels like timing attacks. To truly appreciate the elegance of lattice cryptography, let's look under the hood of ML-KEM, or Kyber. How does it actually work? Let's walk through the setup. Alice wants to create a lock. She generates a matrix A, which is a grid of polynomial numbers, and this matrix is public. She then chooses a secret vector S, consisting of small numbers, and an error vector E, which is random noise. She computes T equals A times S plus E. Her public key is the pair A and T. Her secret key is S. Crucially, because of the error E, knowing T and A does not let an attacker easily figure out S. It looks like random noise. Now, Bob wants to send a message. He turns his message into a polynomial vector. He generates his own ephemeral secret R and error vectors. He computes two values. First, U equals A transposed times R plus E1. This hides his randomness using the public matrix. Second, V equals T transposed times R plus E2 plus the message. This masks the message using Alice's public vector T. He sends the ciphertext pair U and verses. When Alice receives U and V, she uses her secret S to compute versus minus S transposed times U. Let's do the algebra in our heads. V minus S transposed times U is approximately equal to T transposed times R plus the message minus S transposed times A transposed times R. Since T is approximately A times S, the terms T transposed times R and S transposed times A transposed times R are roughly equal and cancel out. What is left is the message plus noise. Because the message bits are encoded to be far apart, for example, 0 is represented by 0 and 1 is represented by a large number, Alice can simply round off the noise to reveal the clean message. This technique, which effectively amounts to encryption by noisy multiplication, is the heart of the post-quantum revolution. However, it is not invincible. Lattice cryptography is strong, but implementation is perilous. One major threat comes from side-channel attacks. Lattice algorithms involve complex operations on large arrays of numbers. If a chip consumes slightly more power when processing a 0 versus a 1, or takes a few nanoseconds longer to process a specific polynomial, an attacker can monitor the power fluctuations of the device and reconstruct the key. This is a major headache for smart cards and IoT devices. The Falcon algorithm is particularly notorious for this. Because it uses Gaussian sampling, essentially picking numbers from a bell curve, the time it takes to find a suitable number can leak the key. The new standards like ML-KEM and ML-DSA use a centered binomial distribution, which is easier to implement in constant time, mitigating some of these risks. There is also the fear of structural weakness. To make these keys small enough for the internet, we use structured lattices, specifically ideal or module lattices. We assume that adding this algebraic structure doesn't make the underlying shortest vector problem easier to solve. So far, this assumption holds, but in the back of every cryptographer's mind is the fear that someone might find a mathematical trick that exploits this symmetry, a sort of Shor's algorithm for lattices. This is why NIST also standardized SFIN-CS+, or SLH-DSA, a hash-based signature scheme that uses no lattices at all, as a fail-safe backup. Looking ahead, lattice cryptography isn't just about surviving the quantum apocalypse. It enables things RSA never could. We are currently in the largest migration in the history of computing. Every server, every browser, every banking app, and every satellite must be updated to support ML-KEM and ML-DSA. This capability is known as crypto agility. The transition will likely be hybrid. Your browser will establish two keys, one using the old elliptic curve and one using the new lattice standard. If the quantum computer appears tomorrow, the lattice key saves you. If a flaw is found in the lattice math next week, the elliptic curve key saves you. Furthermore, the future of privacy relies on lattices. As mentioned earlier, they are the only viable path to fully homomorphic encryption. The industry is racing to hardware accelerate this. Companies like Intel and startups like Zama are building chips that make lattice calculations 10,000 times faster. In 10 years, we might train AI models on encrypted medical data without the AI ever seeing the patient's names. Additionally, zero-knowledge proofs, which allow you to prove you know a secret without revealing it, are maturing rapidly on lattice foundations, promising quantum-secure privacy for blockchain and identity systems. Lattice cryptography represents the triumph of geometric complexity over quantum raw power. It uses the chaos of high-dimensional space to hide our secrets in plain sight. As we cross the threshold into the quantum era, these invisible grids, these lattices, are the only things standing between our digital civilization and total transparency. The math is ready. The standards are set. Now the real work of rebuilding the internet begins.